Hello, Mr. Area, all right? Yeah, good. Okay. So, so given an array of numbers, nums, 1, 2, 3, 4, 5, blah blah blah. Okay. So we want to able to implement two functions. One is to update, define, update with the index to the value. Yeah. So this will change the number at index to value. Right? This is to be very easy. Yeah. And another function would be to sum, to compute the sum of a range and from index to index, right? So basically we want to support these two functions. What's the naive way of implementing it for this one? If we want to update the index with with the value. If this is num, what's your approach? Come on, this will be easy. Huh? You can nums what?
Nums.
Huh? Index equal. What's the time complexity for this one?
1.
1, yeah, perfect. Well done. And then I want to sum the range from index to index. Both are inclusive, yeah. So it's from to. By the way, this means inclusive, okay. And then exclusive is this, yeah. Parentheses, okay. So for example, like, what's the number given this range? The integer. What's the number in this range? Integer.
1, 2, 3. No, 1, 2.
Yeah. And what's the what's the list? What's the numbers between integer between this range?
2, 3.
Yeah, well done. You got it. Okay. So basically, we want to sum the range, sum up the range. What's your approach for this one? We want to sum up the range, given a range from 2. Yeah, this is from. So how can we sum it? You tell me. You don't need to write. I write it for you. So what's your approach?
Don't know.
Sorry?
Don't know.
Didn't know. How do you usually sum it? Just sum it. Yeah. So you can write the loop, right? So okay, you tell me answer equals what? Okay, you fill the blank. For index, yeah, in what? Okay, so what's that? Come on. Okay, you fill the blank. You must know. Okay, come on. Why you don't say it?
This is 1.
Sorry, 1? Come on.
This is answer.
Yeah, this is the answer. Okay, what's this? What? We want to calculate the sum. So at the beginning, what's the 0? Okay, and the range for index in what? For range, yes. Okay, and then what's the from index? From, yeah. What's the to index? Okay, this is a bit tricky. Should I put 2 or 2 plus 1?
2 plus 1.
Yeah, because up to, yeah, 2 plus. And answer equals plus equal what? What are we going to sum up with the numbers here? What are we putting? What are we doing here? Get the number. What's this number? What's this number? If the
1,
index,
2.
if this index, yeah. So what's that?
Index.
Index is index, and what's the value? What's the value? How do we call it?
Num index.
Okay, you know it, right? Why you say you don't know? You know it. Make sense? What's the time complexity for this one? Oh what?
1.
Okay? So we can rewrite this using the sum function. Okay? The Python has this. We can just return sum what? Nums. Okay, you tell me. What should I put in there? And there's a column here. So what should I put here?
Colon minus 1.
That's the. Come on, return some numbers. What? What?
Nums in.
What are we doing here? We want to sum the range, sum the numbers from the 2, right? And so sum nums. What should we put here?
From 2.
From and
2 plus 1.
yeah, well done. Okay. So the time complexity is O(n), okay? Okay, so so given this number, right? So you given this approach, let's quickly put a table here. I'll put a table. Okay. So
Looks
that's
like-
the space complexity, and then that's the update. Okay, update, and then there's the sum. The space complexity for maybe the space complexity for the update, and the space complexity for the sum. Okay. And the first one, we just talked about the first approach. Let's do it N1, which is naive. Okay. The update, we will update is O1, right? The time is what? O1, right? We just say O1. And then what's yeah, okay. And what's this? What's when we sum so what's the time complexity you just said? You just said what? What's the time complexity for this? Number. Okay. What's the time complexity? What's and O1? Okay. What's the space complexity? Are we using any space? Yeah, O1. Okay, this is the approach. Okay. Okay, so the space that's okay. Okay, so look, if there are n updates, so ideally if there are n updates and n sum, n operation of sum, and one of it will be O(n) squared, which is too slow, right? Yeah, O(n) quadratic, O(n) squared, right? How do you pronounce this? O(n)
square.
O(n) squared, and how do you pronounce this?
O(n) squared.
That or sqr or square root of n. Okay.
I like to say it like that.
Okay. Any other ways we can do this? Any other ways? We come up with the data structure before. Remember how can we come? So look, this is too slow, right? We want to get the sum of a range, but this is too slow. So what kind of data structure can we use to make it faster?
We just do these numbers plus and minus this.
Okay, so what's that called? Start with a P. What's that called? What are you doing here? You calculate the sum and then you minus that. What's that called?
That's called
In the beginning, what's that called?
prefix.
Prefix sum. Yeah, prefix sum. So we change this to prefix. Okay, so prefix will be the numbers. Can you write the prefix sum here? We're done. Yeah.
Say
We're done. Yes. We're done. Okay, so look, if we want to calculate the numbers between 2 and 4, so I would need to get the sum of these 4 numbers. That will be 10 minus 1, right? So that will be, so the time complexity for this one is what? If we given this
1.
Yeah, obviously, because this just involves the mathematics subtraction. Yeah? So look, this is 1, right? But okay, so now what's the update? Look, how do we update it? So this is the prefix sum, yeah? Prefix. And then how about if I change this 3 to 4? What would you do? First of all, I need to update the nums using 1. But what happened to this prefix sum? What happened? How do we change this?
We just do the previous one plus this. And
Yeah, I know. But do we need to do that again or from the beginning?
no,
So what number?
we just look at this thing.
I know. But what I'm saying is now I want to change the number 3. Yeah, because we also have this update function. We want to change the number 3 to 4, right? So does it affect any numbers? How do we changing the numbers here?
We put this.
Yeah, the difference. Yeah, 7, and then change and then incrementing all others. Yeah, we're done. Okay. So what's the time complexity for this one? Obviously, if you change multiple numbers, what's that? Yeah, you just need to plus 1 for everything else. Yeah, everything on the right. Okay, that's we're done. Okay. So what's the time complexity for this one? O(n), because this is O(n), this is O(n), plus together is O(n). Because if I change the number here, what happens? If I change the first number, what happens? I need to change all the numbers, yeah? Because it's all affected, right? So this is O(n), right? Look, So look, it seems that either you have O1, O1 here, or O1, O1 here, right? So if there are n operation here, n operation here, one of them will be too slow, right? Yeah? Make sense? Yeah, so today our task is to make one of these quicker than On, okay? Make sense?
One of them.
Yeah. Okay, by the way, the space complexity for these two is O,
One
O,
of them.
On, okay? It's the On.
Smaller than O-N.
Yeah, smaller than On. Okay, so look, because we are using the prefix sum, so the space complexity, space complexity is not, it's not constant anymore, right? We need to update it, and then prefix, okay. Actually, we can just use we can just use one column to represent the space complexity, okay? Okay, so look, if from 2, so we can just do this, return, if it's all inclusive, you want to calculate the sum between this range inclusive, we can just look at prefix 2 minus prefix from -1, right? Yeah, from -1. Yeah, there is -1. But if from is 0, then this will be negative, right? We don't want that. So one way is to add the 0 at the beginning, right? So if we add the 0 at the beginning, then we don't have this problem. So we can just do this from, and then we can plus 1 here, right? Make sense?
Yeah.
Okay. So when we change the numbers, so look, if I want to change these numbers to value, right? Yeah. And all I need to do is to what? This is the value, and I just need to increment the difference. Difference is value minus nums index. Okay. We call this data. Yeah. Data. Okay. Data. Difference. And now I want to change the values to all the values on the right to plus this data, yeah, plus this data, yeah, make sense? That's what you did, yeah. Okay. Okay, now
Biggies.
yeah, okay, let's try. So that's the second approach, yeah.
Bogies.
Still a bit slow, because look, this one sum On, this one update On, right? Look, I have 9 numbers.
But you said to get time complexity under O, and then this is.
On, yeah.
Yeah, that's less than O-N.
Yeah, I know, but look, this is slow. So we won't have these two. We have these two functions, and then each of them has n time. We want to call it
So
n times.
all of this has to be less than O-N.
Yeah, less than On. Yes.
Oh.
No, not the space complexity. Okay, don't worry. Just the time complexity. Okay. So these two are the
This
time.
and this.
Yeah, these two columns, time complexity. If you times n, what happens? There will be n squared, right? Yeah. Look, On is this. This is On. On squared. Yeah. Look, it's going up very quickly. Yeah? When n is 100, it's what? 100. What's that? 10,000, right? Yeah, it's very slow, right? Yeah, you need to iterate 10,000 times, right? So ideally we want to find something under the n, right? Under the n. Maybe here look at log n, right?
But why do you need to times n?
Let's say if there are if I want to call this function n times, right? Make sense? I want to call this function n times.
Why?
Because I said so. I just want to, let's make it faster, yeah? Because look, the problem is that I want to call this function n times, and n times this. N times the update, n times the sum. And look, if this one of them is n, then it'll be, you're making the complexity On squared, right? Yeah, without the d, okay, On squared, yeah? Make sense? Okay, so let's look at these 9 numbers. How about if I tell you that I want to group them into 3s, yeah? And I want to have a block which contains the sum of this block, yeah, or the sum of this block. So it will be array of 3, yeah. Okay, so there are n numbers. So I want the block size with n. Okay, block size will be square of n. And how many blocks are there?
3.
Which is the same as the number will be square root of n. Alright, makes sense because look. Square root of n times square root of n is n, right? Make sense? 3 times 3 is 9. Okay, so what's the sum of these 3 blocks?
6.
15.
And 24.
Okay. So look, sometimes this square root n is not an integer, right? For example, if there are only 8 numbers, you can't separate it, right, into 3 or right? Make sense? It's just a rough estimation. We can allocate the block size of square root of n. So why are these useful? So look, if there are n square root of n blocks, right? So if I want to accumulate to do the sum range, in the worst case, how many blocks I need to cover? In the worst case,
All of them.
all of them. So which is how many blocks?
9.
This one. No, not 9 blocks. Square root of 9,
Oh.
3 blocks, right?
All of them.
Yeah. So when we calculate it, it will be square root of n, the time complexity, right? And when we update it, so how about if I want to update? Look now, if I want to change this number, the 5 to 6, what happened? If I want to change this 5 to 6, what should we do? First of all, we need to change this to 6, and what happened here? Yeah, change it to 6, and what number should I change it? Yes. Yeah, look, I just changed this. I don't need to worry about the rest, right? Yeah. Okay, so the time complexity for this, let's say this is the square root decomposition. Okay. So square root how do you pronounce this word? Decomposition. How do you?
Decomposition.
Don't go around and around. You make me dizzy. Okay, so how do you pronounce it? Composition, yeah? And put a D means the opposite, yeah? Decomposition. Square root of decomposition. So look, the time complexity is all square root of n. Sum will be square root of n as well, right?
That's n.
No. Okay, I make a mistake here. This is to be O1, right? Yeah, because we just update the blocks, right? One block, right?
5 less than n.
Yeah. Look, so if I times On times, so the time complexity, if I multiply this, it will be On times square root of n, right? This is better than On square, right? Make sense?
Mm-hmm.
When we update it, we just do what? We just update it, so it will be O1, right? Yeah? Make sense?
Mm-hmm.
Okay, so okay, so the space complexity for this approach will be what? How many blocks, eh? It will be the how many blocks are we using? So what's the space complexity? What's the space complexity? What's the space complexity? Yes.
Space complexity.
What's the space? How many? It depends. It means how many blocks are we using? Yeah. How many blocks? What's the space one?
N squared.
D or without D?
Squared.
Squared. Okay, so it's space complexity. I have just put it here. Okay, O(n) squared. Okay. So basically, we just need 1. Okay. And then it will be O1. Okay. Okay, so now how do we map? Look, this is suppose this index will be 0, 1, 2, and 3, 4, 5, 6, 7, 8, right? And how do we map this to index here? How do we map this to index 1? How do we map this to index 2? If the block size is 3, how do we map this original index to the block index? Very simple. Yeah. Though it. Any idea? How do we map 0, 1, 2 to 0 and 3, 4, 5 to 1, 6, 7, 8 to 2? What's the common about it? We need to just do what?
Just a list.
What happens if I divide it 3 for 0, 1, 2? All become 0, right?
Yes.
Divided by 3, 4, 5, all become 1. The integer part, right? It's not yet 2, right? Yeah? 6, 7, 8 divided by 3. 2, right? 2 or 2 point something. And what's this? What's the floor? And do you still remember?
Yes.
Floor, this is floor. This is ceiling, right? Yeah, mathematics, this is floor. 3.5 floor equals what?
3.
5 ceiling.
4.
Okay, that's it. So we just need to do floor, the original index divided by block size. Okay? The floor. Then you map to the floor, right? Make sense? Okay, so let's write this. Let's write this. So first of all, at the beginning, I just need to, okay, that's the init function, yeah, init function. And we're taking a num. So first of all, the n, okay, n will be equals to the length of the nums. Alright, and then m, this is the block size, okay, m, block size, would be the square root, yeah, square root. If we want to use the square root, we have to import the mass, yeah, mass dot square root, from mass import square root, okay, yeah, square root of n, and we want to change it, we want to convert it to integer part, yeah, integer part, so we can just do this in, that's basically the floor function, right? And then we want to convert the allocate the blocks at the beginning. The block sum for each block at the beginning, what does it equal? At the beginning, initialize to 0, yes, times n plus 1. Let's make an extra space because sometimes it's not evenly allocated, right? Because I just said the integer, the square root of n, it might not be an integer, and we have to allocate maybe 1 or 2. Yeah, 1 or 2. Yeah. And at the beginning, and then I just need to go through for I in range n, right? This is the original index, and I want to put it in the blocks I. Okay, so tell me. Okay, so blocks what plus equals the numbers, nums I, right? So basically, I want to put the numbers, add the numbers in each block, right? So what did I just say? So the index I goes to in. Yeah, and
plus.
Huh?
Oh no.
What?
Divide.
Divided by, okay, two forward slash means the integer divide, and you will get the integer part, which is the floor. Okay, divided by the block size. Okay, which variable is the block size?
N.
Well done. Okay, and now we have this block size. Okay, so this is the init function, the preparation. Yeah, preparation. Yeah, and now we want to update. Update is simple. Yeah, update. I want to update with the index with the value. First of all, I want to find out which index, okay, so the index, look. So I need to do what? I need to blocks index divided by m. This is the index, converting the index to the block ID, right? Needs to plus the difference. What's the difference? The current value is value, and then I need to minus the previous value, which is nums index, right? This is the difference, right? Yeah. If you're changing the 5 to 6, this will be 1, right? And I want to update the block sum, yeah, with one more, right? Makes sense. And then I just need to update the values again. So nums index equals value. Look, these two lines. What's the time complexity? It's written on the board. What's the time complexity for the update? Which one is it? Look at this. 01. Come on, yes, it's 01. Okay. And to this preparation is all n, right? Because we're going through the n, right? Space complexity on squared. Okay, on squared. Yeah. On plus 1. On, okay? Which is square root of n, okay? Now the most key part is to sum the range. Define sum the range. Okay, come on, this is the last part, okay? Sum range. Let's say from I to index j. We want to sum the range, given this range, I to j inclusive, okay? Okay, at the beginning, let's put the sum in here, in the answer variable, right? Yeah? Okay? And then now let's do this x, this is the pointer, x, okay, this is the position, let's put it in the p, okay? P equals the position, and I. Why it's not reaching the j? When we are currently not summing up to we're not reaching the rightmost part. Okay. So now here, again, this is the number, and we have sum. Which is 6, 15, 24 here. Now, if I tell you, look at me. If I tell you I want to sum this range, I want to sum up the range here. Okay, what would you do? What would you do?
Plus D is a number.
No. I want to sum the range 3. I want to get a sum between 3 to 7 inclusive. 3, 4, 5, 6, 7. What would you do? What would you sum the sum? What would you get the sum?
We only know these numbers.
No, we're given these whole numbers, and I have to tell you this is block sum. Blocks. Yeah, there are 3 numbers. What would you calculate the sum? How would you calculate the sum?
I would just sum all of them.
Then what's the difference than the previous, the first one? Remember, we have this blocks. How would you sum it? Make use of this. How do we make use of it?
We just use that.
Use that, and then we use that to get the sum of this block.
And then just plus this.
Yeah, exactly. Yeah, that will make it faster, right? Make sense? Yeah, because because these two, yeah. At most, we are traversing one block, the entire block. We don't need to go over each element in each block. And for the rest, yeah, these two rest, at most it will be roughly square root of n times 2, right? Yeah, let's make it the most and the worst it will be this. So the time complexity will be like that. Okay? The time complexity. Why is that? Because they are square root of n blocks, right? Roughly, okay? And then for the rest, which is not inside, which is not covered in the entire block, I can just do this sum, yeah, by individual number, and that, let's say in the worst case is 2 times the square root, but it's less. So this time complexity will be O square root of n. That's why we have here, right? So look, now how do we check if it's currently, if x is here, and then x plus the m size is smaller than j, right? It's smaller than the j. Then we can use the block sum, right? We don't need to go through each number in the blocks because we already pre-calculated the blocks, the sum in the block, right? Okay. While p smaller than j, then we say if p modulus block size equal 0, and it's covered. This block is totally covered. So p plus m smaller equals j. Then we can just add the sum, right? Answer, right? Plus equal the block size, the sum will be blocks. The block sum of current is p, right? P will be converted to the block size. So this is the block size. And then we need to jump the entire block, right? Because look, we already here, we know this number is 15 and covers 3 numbers. And once I added the sum, I need to jump to the next block, right? Make sense? I don't need to jump one by one. I can jump to the next block. So p plus equal jump by m unit, yeah? Plus equal. Else is that it's not covered. Then I have to edit. The current number, right? So answer plus equal. The current number is nums. Nums what? Nums p, right? Nums p, and then p plus equal 1. Yeah? We move by one by one, right? Okay, am I right? Return what? Come on, this is the easy part.
Return answer.
Yeah, return the answer. Yes. Make sense?
Yes.
Make sense?
Yes.
Okay. Do you really understand? Do you want me to test you for a little bit? Give you a little bit challenge, okay? Come on. Okay, that's easy. So can you explain to me what's this part and what's this part? And that'll be it.
Oh man. Okay, so answer plus equals the blocks. That p thing for the blocks divided by the size of the blocks.
Yeah. Okay. So look, I want to calculate the sum from 3 to 7. From 3 to 7. Okay. This is p. Yeah.
So the answer plus is the block. Yeah, in that.
So I'm 3 here. Yeah. And then look, I'm here. I move it to here. And then look.
And that's the block.
Yeah, block sum. I here, and I move it, jump to next one, eh?
And then we
Otherwise, if it's not covered by entire block, then I have to add the sum 3 and 7. So basically the sum will be 3 plus 15 plus 7. Okay, the 15 part is here. The 3 and 7 part is here. Got it? Make sense? Yeah. Is it clear? Is it clear? So the individual, if this individual is not covered by the block, yeah, it's not covered by the block like in the range. Okay. Because look, we want to calculate the sum between these two, right? And it only covers one entire block, right? If it covers the entire block, then I can add it. I can speed up the process. I don't need to add the numbers here, right? Because I already know that, yeah. Make sense? And but this leftover individual, I just add it, right? So the times complexity I just said, because they're at most square root of n blocks. So the worst case is square root of n plus an individual. Yeah, this individual cannot be more than 2 times square root of n, right? So altogether it will be O square root of n. Let's this part, the sum of this part. Okay, update we will cover this. Okay, so now the very last bit. Okay, so look, which one is bigger? Which one is bigger? Sometimes we have this, yeah, log n. Which one is bigger? It's a bit tricky, okay? Because look, this is square root of decomposition, and in the future we're going to talk about some other trees, some other techniques like segmentation tree, Fenwick tree, which has the O log n in both methods, yeah, update and sum. Okay, so can you tell me which one is bigger? If you don't know, we can always plug in a value. Let's say let's plug in n equals 100. What square root of 100?
10.
Okay, so what's this number? Log 2 to the 100 to the power of 100. 2 to the power of what? Is roughly 100.
2 to the power.
How many 2's you need? How many 2's you need? Come on. How many 2's you need?
Wait. 1, 2, 3, 4, 5, 6, 7.
7. If it's 7 is what? 2 to the power of 7 even.
128.
Okay, 2 to the power of 5. 2 to the power of 5. 4, 16, 32. 62, yeah. So it's between 64. It's between 64 to 128. So the number is 2 to the power of 6 point something, yeah. 6. So it's roughly 6 point something. So which is faster? Which is faster? Yeah, slow is faster. So, but still, this is quite good. Okay, okay, makes sense. Today we complex this O square root of n, and if we plot it, this is O(n). This will be O log n. This will be okay, roughly okay, O(n) square, and O. This will be more a little bit more than this, yeah, between, yeah, got it, yeah. This will be square root of n. Okay, make sense?
Yeah.
Okay, that's it for today. Good job. Bye bye. Bye bye.